So say we are given an irreducible polynomial p over the field f, and alpha is the root of the polynomial. So you can do this operation and get this field f with adjoined with alpha. And this immediately implies that degree of f adjoined with alpha over f is precisely the degree of irreducible polynomial. So say the degree of irreducible polynomial is n, then we already know that the basis of this is this x bar square, x bar cube, all the way to x bar n minus 1, where this x bar is nothing but x plus our irreducible polynomial. So first notice that this q, zeta over q is 2, and this corresponds to the minimal polynomial, this x square plus x plus 1 over rationals. So this is rationals here, this is rationals here. Again, so this zeta is nothing but cube root of unity. So exponential of 2 pi I over 3. So this is cube root of unity. So now consider another extension like this. You are joined 2 1/3 to rationals. So this degree of extension over rationals is 3. So we have this minimal polynomial x cube minus 2 over rationals. So again, notice rationals here and rationals here. So we can extend this argument to here, that is rationals adjoin the zeta to it and 2 1/3. This is over rationals adjoined with 2 1/3 is 2. So again, what is a minimal polynomial? You can consider this as the minimal polynomial over this rationals adjoined with 2 1/3. So you have to make sure that this is irreducible polynomial here. So for that you will have to show that zeta does not lie in rationals 2 1/3, and this is easy to show because this is a complex number and this is just real numbers. So now rationals adjoin 2 1/3 to it and our cube root of unity over rationals. This you can write it like this. So first you have this portion, this one right here. So this is degree of extension is 2. The second portion is rationals 2 1/3 over rationals. This is precisely here. So this is 3. So 2 times 3 will yield 6. So rationals adjoin 2 1/3 and zeta to it, and then this over rationals, this degree of extension is 6. So notice that you have this polynomial x cube minus 2 over rationals, and splitting field for this is this. So now you can all see that the degree here is 3, but this degree of extension is 6, because we have to consider one irreducible polynomial at a time. So if you consider this here, this is not irreducible in rationals 2 1/3, does have a root. So the splitting field for this is like this. So this is how it splits. So it splits like this, and we know the splitting field is this. You have just adjoined the roots, this and this zeta, to it, and you will get all 3 roots. So you have 3 roots, 2 1/3, zeta times 2 1/3, and then zeta square times 2 1/3. So you have 3 roots. All 3 roots are distinct. Now you can say that this adjoint 2 1/3 and zeta to rationals over rationals is a Galois extension. So again, for this, notice this, that k over f is Galois if and only if k is splitting field for some polynomial f in f of x. So we are taking k as our splitting field. To q you have adjoined 2 1/3 and zeta to it, and our f is simply the rationals. So f is simply rational. So what is the separable polynomial? The separable polynomial was this, x cube minus 2. You can see its roots are distinct roots. So we have, this is a Galois extension. So what are the group of automorphisms of it? So the group of automorphisms which fix rationals, or you can say this is the Galois group which fixes rationals and automorphisms of rationals adjoint root 2 and zeta over rational, this is just S3. So this is just the symmetric group 3, because this is just generated by permuting the three roots. So you have three roots, 2 1/3, zeta 2 1/3, zeta square 2 1/3. So your Galois group is just going to permute these three roots of our irreducible polynomial. So since it's just a permutation group, therefore you have S3, just the permutation group. Now there are two generators of this group. One is var phi and another is phi. So what are these two generators and why there are two of them? So first is var phi. So var phi will act on this irreducible polynomial x cube minus 2. So it will send 2 1/3 to any of the three roots, 2 1/3, zeta 2 1/3, zeta square 2 1/3. So if you want to take a non-trivial map, we will pick one of them which is not just 2 1/3. So this var phi acts on this irreducible polynomial. What about phi? So phi also acts on an irreducible polynomial. Phi acts on this irreducible polynomial corresponding to zeta. So notice that you have a splitting field and you have two things there, 2 1/3 and zeta. So we are considering two irreducible polynomials here, one corresponding to zeta and one corresponding to 2 1/3. So now corresponding to this, the root is, this has two roots, one is zeta and second is zeta square. So this zeta either sent to zeta or zeta square, which is acting on the roots of this, permuting the roots of this irreducible polynomial. So more precisely, let us consider var phi as 2 1/3 is sent to zeta 2 1/3, zeta is sent to zeta, and phi 2 1/3 is sent to 2 1/3. So it doesn't touch this. Obviously it cannot touch this because 2 1/3 is not a root of this, where zeta is sent to zeta square. So we have taken non-trivial permutations here and here. So now let us see the Galois correspondence. So your S3 is generated by two elements, phi and var phi. So you have phi and var phi, and you have these subgroups here, one corresponding to var phi, one corresponding to phi, then one corresponding to phi var phi, then another corresponding to phi var phi square. So you have to check, these are different elements. So all this computation you can find in Dummett and Foote, where it is explicitly computed how what are these elements are. So corresponding to var phi, what is fixed? So var phi just fixes zeta. So this is what is fixed. So group of automorphisms of rationals 2 1/3 and zeta, which fixes zeta. Var phi does that. And what does phi do? Phi fixes 2 1/3. So phi corresponds to rationals 2 1/3 because it fixes 2 1/3 in the automorphisms of this. So again, if you see phi var phi, so this will fix zeta 2 1/3, and this phi var phi square will fix zeta square 2 1/3. So you have the correspondence. So you can find all the details of fixing them and page 545, second edition of Dummett and Foote. So you have this. Again, since both these groups are going to generate S3, so everything is fixed here. So the entire group of automorphisms of this Galois group is generated by this. So now we want to find out what extensions are Galois. So we know this rationals 2 1/3 zeta over rationals, this is a Galois extension. But what extensions here are Galois? So first thing is that let us look at this extension. So k over f is Galois if and only if k is splitting field of some separable polynomial. So for example, taking f this as rationals and k as this, we have a separable polynomial x square plus x plus 1. So this extension is Galois. So this extension is Galois, and degree of this extension is 2 because 2 is the degree of this polynomial here, and this is irreducible polynomial over rationals. So this is fine. You could have also seen directly from here. So this var phi, you can compute it. I mean, this has to be checked. This var phi is a normal subgroup of this phi comma var phi. This is a normal subgroup of the subgroup generated by this. So the group generated by this is group of permutations S3, and this var phi is actually a subgroup of this, which is a normal subgroup. In fact, this is the only normal subgroup. So again, you can check that var phi is 1 phi square. The order of this is 3. Order of S3 is 6. And so this is half of this. So this is a normal subgroup. In fact, this is the only normal subgroup. This is not a normal subgroup. This is also not a normal subgroup. This is also not a normal subgroup. Now these three are not normal subgroups. So H is a normal subgroup of G if and only if KH over F is Galois. So these three we are saying are not normal subgroups. Obviously you will have to compute it to show that these are not normal subgroups. That means these three are not Galois extensions. This is not a Galois extension. This is not a Galois extension. This is not a Galois extension. So let us write it like this. So this star means that not a Galois extension. So these are not Galois extensions, but they are still extensions. So this is extension of degree 3, this is extension of degree 3, and this is again extension of degree 3. And all these three extensions come from the same polynomial, which is x cubed minus 2. But you can see that, again you can see that this is not a Galois extension. Precisely because if you just look at this polynomial x cubed minus 2, then you can see that this is not a splitting field. For example, for this case, it just has one of the roots, 2 1/3. It does not have the other two roots. Similarly here, this is not a splitting field for this polynomial because it does not have these two roots, 2 1/3 and zeta square 2 1/3. And this is not a splitting field for this polynomial because again, it does not have these two roots, this root and this root it does not have. But notice that if you just compute this first, you compute this is not a normal subgroup, this is not a normal subgroup, this is not a normal subgroup, that you immediately know that this is not a Galois extension, this is not a Galois extension, and this is not a Galois extension. So if you use this result that say this is F and now this is K, this is K and this is F, so this is not Galois, and that would immediately imply that there is no separable polynomial F in rationals whose splitting field is this rationals adjoint to 2 1/3. So notice that this we can compute because this is a finite group and you can check case by case, put in a computer and check case by case. For example, you can just check case by case that this is not a normal subgroup of this. So once you check this is not a normal subgroup, you already know that this 2 1/3 adjoint to rationals is not a splitting field for any polynomial. So you cannot check infinitely many polynomials here to say there might be some polynomial for which this is a splitting field. This result here that this is not a normal subgroup of this immediately tells you that this cannot be a splitting field for any polynomial like this.